Uh, well, good evening to everyone. I would like to thank the International Institute of Physics for hosting Vortex 2017 and making it available, this fantastic team of people that are collaborating with us and making life easier for the organizers. Thank you. Well, my talk would be called, instead, I think it's a simple title, would be Viral States and Fermi Arcs in Parabolic Bands. That's the main subject. Well, this is some of the collaborators throughout this work along the years. Some are in the audience. There are some publications about it, and I want to make here a point. Oops, just press here. Ah, okay. Yep. Oops. Okay, let's go. Okay. Well, first I would like to call your attention to two aspects important for my presentation. One is the linear Dirac spectrum, okay, found in ARPs in so many materials nowadays, from topological insulators, graphene, cuprate superconductors, iron-based superconductors, the vial semi-metals, which means that particles found in ARPs that display dispersion relation proportional to the momentum. This is an example of topological insulator, and we see here in ARPs directly this spectrum, which is all over. Second thing that I would like to call your attention is to the Fermi Acts that now are being found in these topological insulators and vial semi-metals, but they were found before in the bulk in the underdoped phase of the high-TC cuprates. So for instance, we see here the energy Kx, Ky, we see these arcs, and the pseudo gap, for instance, is vanishes at the nodes, and it's higher here, and so forth. They go in the edges, but they are clear sign of underdoped superconductors. Okay. Yeah, okay, this one. Well, I may go beyond my time because of these mistakes, but I would like to summarize everything in a single sheet, okay, a single slide. So my point is very clear here. The linear Dirac spectrum is a general property of electronic systems in layers and surfaces that also exist in parabolic bands. So this idea that crossing bands is needed for a Dirac spectrum is not true according to this point of view. You can find it in parabolic bands. There is a magnetic field by motion of carriers along the layer that are very important in this framework here. Usually in the Drude Sommerfield, it's totally ignored. You don't care about magnetic field generated by electrons inside the metal. But here we'll see that they are fundamental because they create this magnetic field. This magnetic field goes around the layer, and the streamlines are closed. You cannot break them. So this already you see some kind of stability here, and we see that this is the beginning of the description of topological states in layers. If you have a periodic potential crystallographic potential in the layer, you see that the Fermi surface for this problem here becomes just a Fermi Acts. It's very simple. Okay, so the magnetic most important, the magnetic interaction is attractive between particles that have the linear Dirac spectrum. Okay, I'm not saying that it does not exist. It exists, but you don't need bands crossing. I mean, at least in this framework here. Okay, so the general idea here is that we are going to think about in terms of this Hamiltonian with a kinetic term, a field energy, and a potential energy. The kinetic energy is this standard theory here that we all know, the momentum times psi squared. That's, you see, is what I mean by parabolic. Okay, we have a field energy that is the magnetic energy. But this magnetic energy is a function of psi, because what I mean is that when the particles run, they create a current, and this current creates a magnetic field, and this gives you an energy. And you have a crystallographic potential, which is periodic in some crystallographic, in some structure. Okay. Well, the first thing to say is that about the Weyl equation, that is a common tool. And this equation is written as sigma p psi equal to E times psi. My starting point of view here is that this is not cannot be a Hamiltonian equation, okay? Simply because sigma is a spin here, and sigma p is a pseudo scalar. Okay, let us review in one page about symmetries. So it's good we take the Newton's law, which is written there, okay, in presence of a magnetic field, and we see that if we reverse the time or reverse the parity, the position, the electric field changes. Does not change in time, but changes the magnetic field, and the other way, the electrical field. Okay, so we see, for instance, that if position changes, momentum changes because it's dx dt. Okay, let's concentrate on position, but angular momentum does not. Okay, and so spin does not. So it means that sigma p goes into minus sigma p, and this is not possible to be Hamiltonian. Okay, just to point out here. Okay. So, I mean, people in graphene, they know about that. And in fact, they write the Weyl equation, okay, which is here. But in their case, sigma is not spin. It's just an isospin. Just represents hopping from one triangular lattice into the other, okay? Type A and type B. So they are safe with that. That can be a Hamiltonian. Okay, but it turns out that 6 years before the discovery of graphene, Abrikosov himself wrote a paper trying to explain the linear magnetoresistance in the chalcogenides. Okay, and his assumption was that his assumption was that his Hamiltonian is sigma times p, is exactly the Weyl equation. Okay, would you change it? Você muda para mim? Is there one missing? Is this one? Okay. Okay. So we have to interpret the Weyl equation again. Okay. So the Weyl equation you write like this. Okay. But then I mean, if you see the parity transformation that takes x into the minus x can be a rotation plus a reflection in the plane. So everything is invariant under rotation. So we just concentrate on the reflection operation. So it means that that energy is not an energy. You really have to add up something that flips sign from one side, from top to bottom of the layer. I'm considering here just a layer, okay, for simplicity. We're moving backwards. I've checked before the talk. No. I think this one, let's see if it works now. Ah, come on, it's not working. Okay, let's see. Okay, so that's this parameter E should be interpreted in that way, okay? And then we go to, okay, let's try to solve this the value equation interpreted in this way for a layer. So we get the solution, that's the solution, okay? And then just keep in mind that K is the momentum in plane, okay? K plus is K1 plus IK2 that appears there. And the interesting thing is that you have exponential decay from the layer. This K3 is really the momentum minus theta squared. Theta is a parameter that naturally appears here that separates modes that are scattered in the plane and modes that are trapped in the plane. So modes that are trapped in the layer, they are not really strictly two-dimensional, but they decay exponentially away from the layer characterized by this K3 parameter, and this theta parameter appears naturally. So that's the interpretation I'm giving to the value equation. Okay, now comes the important ingredient here. I'm a little bit, I missed this. I missed this slide before. Here comes the main ingredient of this talk that allows me to go to these results, is that the kinetic energy, which is the simple expression there, can be expressed as the sum of three terms. That's a theorem, okay? That's mathematically proven. It's not a matter of taste. So what do you get here? You get the Weyl equation squared, okay? You get the magnetic interaction, the local field times the spin properties, local spin of this order parameter, which has to have two components. And you also get a surface term, which is the Rashba term. So what I'm saying here is nothing less than the Rashba term and that local magnetic spin interaction and the Weyl equation are inside the kinetic energy. Okay? So once I have that, I can play around with this expression and try to find some results out of it. Okay? In fact, the Rashba equation that is here appears just as in this three-dimensional integral. You can transform it easily as a surface integral that counts the Rashba term above and below the layer. Okay, so one first limit. Let us consider two very simple ones. Let's ignore the magnetic field. So ignore, there's no magnetic field. Let's throw this away, okay? So that's the Weyl equation. But the Weyl will just is this theta parameter times psi. So essentially I get this, okay? The other one, which is a surface term, okay, I can play games using the Weyl equation, and it becomes the Laplacian of rho. Okay, so that's the theory that I have at the moment when I throw away the magnetic field. It turns out that if you take psi from that solution of the Weyl state, you get this expression here, okay, square root of k squared minus theta squared, which means that if kappa is much the momentum is much larger than this cutoff, I get exactly the Dirac cone. Okay, so the Dirac cone is I can obtain it. I can say the following: if I take the Rashba interaction above and below the plane, and demand that I have a Weyl state, I get the Dirac linear dispersion relation, okay, which arises here exactly in this way, okay, out of the kinetic energy. So, if you go to momentum, transform that energy energy-momentum, you have this dispersion relation here, Ek theta squared, square root of k squared minus theta squared plus 4 square root of k squared minus theta squared. Okay, so that dispersion relation has it blows up at theta. Okay, but no problem with that because the density of states in 2 dimensions will not make this harmful. You have a term proportional to k times the square root of k. It vanishes, and then you have this linear behavior. So you have a local minimum here, which means that if you fix the chemical potential, you have 2 possible values of for the Fermi momentum. Okay, so the Fermi momentum is not a circle, but it's a ring. Okay, and that's what's drawn here for several values of theta. And if you go here, you see this ring. Okay, and if you take the first Brillouin zone, and if you assume that it's beyond the first Brillouin zone, a little bit above half filling, you are by the Bloch's theorem, you are going to break. You have the set of gaps, and then finally, what you get here are Fermi arcs. That's what I'm referring as Fermi arcs. So it comes naturally from the kinetic energy. Okay, so now the most amazing thing is that we go back now to that expression, kinetic energy plus field energy, with the 3 terms plus the magnetic interaction. Okay, so for the moment I will ignore the lattice potential. Okay, now it turns out that this new expression of the kinetic energy gives me a new expression of the current. Okay. So we are going to consider here, for simplicity, the case that theta is equal to 0. It means that sigma d psi is equal to 0. It means that these are states of 0 helicity, because sigma d, p is the operator of helicity. So this is 0. Okay, and now you see something very amazing, okay, taking place. If this is equal to 0, because I'm assuming that theta is equal to 0, my current is exactly the curl of this quantity, which means that if I go to my program of the Ampere's law, I can solve it exactly, and that's the value of the magnetic field. Local magnetic field is totally known, okay? And it carries that important negative sign, which means that if you put it up in the kinetic energy and sum up with the field energy, I end up with this expression for my energy, which is this term here, minus 1 over 8 pi h squared. This term here is nothing but the linear spectrum, the Dirac linear spectrum. So it means that particles with 0 helicity, okay, they form a Dirac cone, and the magnetic energy is attractive among them. These are, I call them topological equations. They are really amazing equations. Solution of first one, which would be the Weyl equation, but with theta equal to 0. The local field is known. If you solve these equations, you immediately know a solution of Maxwell's equation. Okay, it means that the divergence of H is equal to 0. Okay, which means that they are closed streamlines. And if you look more carefully, you'll see that they go around a layer. So that picture that I showed you in the first slide is true. And you also have some properties like they break time and reflection symmetry, which means that you can find a solution with the opposite sign, magnetic, and if flipped order parameter. So it means that I have a ground state that can have a magnetic field rotating in one way or in the other, okay? And I don't break the properties of symmetry of the kinetic energy. So these equations that I just showed you, they are generalizations of the Abrikosov-Bogomolny equations for one order parameter, okay? That led to discovery of vortices. So here I'm talking about a set of equations that are in 3 dimensions, okay? And they will lead you to ischemions and also vortices in case of a magnetic field. Okay, if you go to 4 dimensions, these equations can be generalized, and they're exactly the Seiberg-Witten equations that lead to massless monopoles. So it seems that this set of first-order equations are associated deeply with topology. What's topology here? It's simple. I mean, in the plane, I have a periodic lattice that I assumed, I mean, some box, okay, that I wrap around, and I have a torus. But in each point of this torus, a local magnetic field is defined, a vector. So I have mapping from a torus to a sphere, okay? And this will characterize me Chern number, which will be an integer, and I'll be able to have non-trivial, I'd say, inhomogeneous solutions that will not be able to decay into other ones. I mean, as long as this magnetic field is there, and it's not destroyed by collisions, okay? So this expression for the kinetic energy is general. I mean, I'm thinking in terms of second-order quantized fields, but you can think in terms of Ginzburg-Landau theory, okay? In the past, we tried to apply it to LAO-STO interface, that we believe that this is the case. This system has something very funny. You apply a magnetic field here, and you get a torque perpendicular to it, okay? We believe that this can be explained by this 3-term kinetic energy decomposition, assuming that we have some anisotropy between the 2 sides of the system. And so we try to describe the data of Lu Li and co-workers. That's the magnetic moment, that's the torque. In red is our theory, in black are the points, and it was okay. So that's what I had to say. Thank you very much. Sorry for the delay.